So you've shared this material on intuitionistic type theory, and it's really fascinating stuff, especially from a philosophical perspective. It's like less of a logical system and more like, rethinking how we even think about logic and math and even programming, wouldn't you say?
Yeah, absolutely. Intuitionistic type theory, or ITT, as it's often called, it aims to be the kind of the constructive counterpart to what we have in classical mathematics, like the Zermelo-Fraenkel set theory.
Right. And it rebuilds the foundations of math, but with a focus on how we know things rather than just what's true.
Exactly. It's about the process of getting to knowledge.
Okay, so let's unpack this a bit. Constructive. What's the big idea behind constructive mathematics?
Well, at its core, constructivism says that to really prove something exists mathematically, you can't just assert it, you have to show how to build it or find it. And ITT really takes this to heart.
So it's not enough to say, oh, this mathematical object must exist because if it didn't, there'd be a contradiction. You actually have to show me how to, construct it step by step.
Precisely. And a really key way to understand ITT is to see these mathematical concepts, numbers, sets, functions, through the lens of, programming concepts. Think of them as data types and programs.
Interesting. So it's a shift from thinking about these things as existing abstractly to thinking about them as something you could, in principle, compute or construct. That's a pretty big change for a lot of philosophical views of mathematics.
It is. And a really, truly mind-blowing aspect of ITT is this thing called the propositions as types principle.
Propositions as types. Okay, tell me more.
It's the idea that a proposition, like a statement that can be true or false, is actually the same thing as the type of its proofs.
Wait, a proposition is the type of its proofs. Okay, that's wild. So instead of truth being this abstract property out there, you're saying that knowing a proposition is the same as having a blueprint, a program for how to prove it. That's like turning centuries of logical thought on its head.
You got it. In traditional logic, you have a proposition. It's either true or false, end of story. But in ITT, a proposition actually tells you what counts as evidence for its truth. And that evidence, the constructive proof, is an object of a particular type, the very type that the proposition is.
Wow. So proving a proposition becomes the same as finding an inhabitant of that specific type. If a type is a specification, then a proof is something that meets that specification.
Exactly. And this extends this thing called the Brouwer-Hating-Kolmogorov interpretation of intuitionistic logic, which is already dealing with constructive proofs. But ITT goes further by giving us a definition not of what a proof is, but also what a constructive mathematical object is.
So it's this really direct, almost computational way of understanding math.
Yeah, that's a good way to put it.
Now, the material you shared is quite in-depth, covering everything from the basics of ITT to these things called mathematical models and different versions of the theory. It's clear that we're dealing with something really deep here.
Oh, absolutely. The Stanford Encyclopedia of Philosophy entry in ITT is a goldmine. It goes through the whole system, the idea of propositions as types, the basic structure of ITT, how it's extended, the philosophical ideas behind it about meaning, how it relates to other mathematical systems, and different flavors of the theory.
So our mission, if I understand correctly, is to delve into the heart of ITT, specifically the parts that would resonate most with your background as a philosopher, right? We're looking for those aha moments, those surprising insights, without getting lost in the technical weeds.
Exactly. We want to capture the essence of what makes ITT so unique and important for understanding logic, math, and how they relate to computation. And of course, we'll be looking at it through that philosophical lens.
Awesome. So let's start with how ITT changes the game for logic itself. It's not just about assigning true or false anymore, is it?
No, not at all. One of the big things ITT introduces is this idea of explicit proof objects.
Okay, proof objects, what are those?
So in traditional logic, when you talk about a proof, it's often seen as this abstract sequence of steps, these inferences you make. Mm-hmm. But in ITT, a proof is a concrete mathematical object, a construction. And it's this object that actually serves as evidence for the truth of a proposition.
So it's not just a chain of reasoning, it's like a thing, an object. And this object is what makes the proposition true.
Exactly. And because these proof objects have computation rules associated with them, it gives logic this very direct computational interpretation.
I see. So how does ITT fit in with the history of logic? The material mentioned Brouwer's intuitionism and Russell's type theory.
Right. So ITT draws inspiration from both of those. From Brouwer's intuitionism, it takes its emphasis on the constructive nature of mathematical truth. You have to be able to show me how to build the thing.
Right, right.
And from Russell's type theory, it inherits this idea of organizing mathematical entities into types to avoid those nasty paradoxes that can pop up.
Yeah, those paradoxes are no fun. So ITT uses types, but it also uses this propositions as types idea, which is pretty unique, right?
Absolutely. And the foundation of it all is this thing called typed lambda calculus. It's a way of writing down functions and being very precise about what kinds of inputs and outputs they can have, those types. But what really sets ITT apart is that it puts the propositions as types principle right at the center. And that connection was first observed by Curry, but only for propositional logic.
And then someone else extended it to predicate logic?
Yeah, Howard and De Bruyn took it further by bringing in these things called dependent types. And that's where things get really interesting.
Dependent types, huh? Those sound powerful. It's almost like the category something fits into isn't fixed, but it depends on the specific properties of that thing. Is that on the right track?
That's a great way to think about it. Dependent types are like families of types, and which family something belongs to depends on some value. Like, you could have a type for vectors of lengths n, but the exact type depends on what number n actually is.
Right, so the type itself is like parameterized by this value.
Exactly. And in ITT, dependent types are what allow us to represent predicates. So being a prime number applied to a number x becomes a type that depends on x. And an inhabitant of that type for a specific number would be a proof that the number is prime.
So the logic of statements like, for all x, px, or there exists an x such that px is reflected in how these dependent types are built and used.
Yeah, you got it. They're crucial for interpreting those quantifiers. So universal quantification, that for all idea, becomes a dependent product type. It's like a function that says, give me any element of this type, and I'll give you back something that satisfies this property.
And existential quantification, the there exists idea.
That becomes a dependent sum type. It's like a pair, saying, here's an element of this type, and here's a proof that it satisfies this property.
I see. So ITT doesn't just stop at logic, right? It goes on to incorporate these fundamental mathematical structures, too.
Yeah, for sure. It includes basic types like natural numbers, 0, 1, 2, 3, and so on. And it even has this type of small types, which is often called a universal. It lets us talk about types themselves within the system. And then you have things like well-founded trees, which means it can handle a good chunk of intuitionistic mathematics, including intuitionistic number theory.
That's pretty cool. The material also mentioned that ITT is formulated using this thing called natural deduction with specific rules. How does that connect back to the idea of these proof objects as constructions?
Right, so ITT is presented within this natural deduction framework. And for each type, which represents either a logical connective or a mathematical structure, there are these rules. Formation rules tell you how to define the type. Introduction rules tell you how to construct things of that type. Elimination rules tell you how to use things of that type. And equality rules tell you when two things of the same type are considered the same.
Okay, so these rules are like the blueprint for building things within ITT.
Yeah, exactly. And the really cool thing is that the introduction rules often correspond directly to the steps you take in a constructive proof.
So the proof objects, those concrete things we talked about, they're built according to these introduction rules.
Exactly. They're the terms, the objects, that inhabit these types. For example, an introduction rule for the product type, which represents and, allows us to form a pair if we have an element of each of the types being combined. That pair is the proof object for the and statement. And when we bring these proof objects into the natural deduction calculus, it basically turns into a typed lambda calculus with dependent types. And the equality rules become computation rules for manipulating those proof objects.
That's really elegant.
Yeah.
Okay, now let's get to the really interesting part, the philosophy behind all of this. You said earlier that ITT is an interpreted language, which has some big implications for how we understand its meaning and validity. Can you unpack that a bit?
Sure. So what that means is that ITT isn't just a bunch of symbols that we manipulate according to formal rules. It actually has meaning built into it, and that meaning is tied to how we use it. The act of making a judgment, like saying something is a type or that a term has a particular type, and the act of providing a proof, they're all inseparable from their meaning. And the way we explain that meaning is through how we compute with these things, how we get to their simplest forms.
You keep mentioning these simplest forms, like the most basic, irreducible versions of things. What are those called?
Those are called canonical forms. They're the fully evaluated forms, like the final result of a computation. For example, the canonical form of a natural number is either 0 of v, or the successor function applied to another canonical natural number. And the canonical form of a function is a lambda abstraction, which is basically a function that's ready to be applied.
Okay, so the meaning of something in ITT is tied to how it computes, how it reduces down to these canonical forms.
Precisely. And these explanations of meaning, they're considered pre-mathematical because they try to give us an understanding that doesn't rely on some other more fundamental mathematical system like set theory. It's the different way of justifying the consistency of a logical system rather than just building models for it within set theory.
So it's like ITT is trying to stand on its own feet, so to speak, when it comes to its foundations.
Yeah, exactly. It's trying to provide its own justification.
Now, the material also mentioned that ITT is something called predicative and that it's different from Russian constructivism because it rejects something called Markov's principle. What's the philosophical significance of those distinctions?
Okay, so predicativity is a restriction on how we define things. It basically says you can't define something in terms of a collection that includes the very thing you're defining.
Right, to avoid circularity.
Exactly. ITT sticks to this to avoid potential paradoxes. Now, the rejection of Markov's principle is another key difference. Markov's principle basically says that if something can't not exist, then it must exist.
Interesting. So if showing that something doesn't exist leads to a contradiction, then it must exist.
Yeah, but the catch is you don't actually have to show how to construct the thing. You just show that it can't not exist. And ITT's hardcore constructivism says, nope, you got to show me how to build it.
So it's a stricter form of constructivism.
Absolutely.
And all of these foundational choices, they shape the kind of mathematics you can actually do within ITT.
Oh, yeah, for sure. They define the boundaries of what's possible within the system.
Now, it seems like ITT isn't just a theoretical playground. The material mentioned these things called proof assistants, like NuPRL, Cook, and AGDA. What are those, and what's their connection to ITT?
Right. Those are computer systems built on the principles of ITT, or systems very closely related to it. They allow us to formalize complex mathematical proofs and check the correctness of software with a very high degree of rigor.
So they're like really powerful tools for mathematicians and computer scientists.
Yeah, and the fact that we've been able to formalize major theorems, like the four-color theorem, using these tools, that really shows the real-world impact of ITT.
Wow. So there's this deep connection between constructive mathematics and computer programming within this framework.
Definitely. The act of constructively proving a theorem often ends up being the same as writing a program that actually computes the result. The proof itself is the program.
That's fascinating. Okay, I want to dive a bit deeper into this propositions as types principle. It's such a central idea, but it's probably not immediately obvious to a lot of philosophers. How does this correspondence work with those basic logical connectives we use, like and or implies and so on?
Sure. So the basic idea is that for every logical proposition, there's a matching type. And the objects that belong to that type are precisely the constructive proofs of that proposition. This is what's known as the Curry-Howard correspondence. And these proof objects, they're not just abstract derivations, they're pieces of evidence, the things that make the propositions true.
Earlier, you mentioned the example of equality. Could you go over that again to illustrate this correspondence?
Sure. So let's say we have the proposition that two natural numbers, m and n, are equal. In ITT, this corresponds to a specific type called the identity type. And this type only has an element in it if m and n are actually equal. The canonical proof of m equals m is a special element of this type, usually called reflexivity. But if m and n are different, then the identity type for them is empty. There's no way to prove a false equality.
So the type itself reflects whether the proposition is true or false.
Exactly. And dependent types, they make this whole thing even more powerful because they allow propositions to be about specific things. Like, the proposition x is prime depends on what number x is. Using dependent types, that proposition becomes a type that's only inhabited if x actually is prime, and the inhabitants are the proofs of its primality.
That's really cool. So what about the other logical connectives? Do they all have counterparts in the world of types?
They do. They're interpreted as type formers.
Okay, so how does that work?
Well, for example, bottom, which represents a proposition that's always false, that corresponds to the empty type. It has no elements because there's no way to prove something that's always false.
Makes sense. What about top, the proposition that's always true?
That corresponds to the unit type, which has just one element, a trivial proof. And then you have disjunction, which is or. That corresponds to a sum type. So a proof of A or B is either a proof of A or a proof of B, but you have to say which one it is.
Right, you can't just say one of them is true. You have to specify which one.
Exactly. And then conjunction, which is and, that corresponds to a product type. A proof of A and B is a pair, a proof of A and a proof of B. And implication, that's like saying, if A, then B, that becomes a function type. So a proof of A, then B is a function that takes a proof of A as input and spits out a proof of B as output.
So these type formers really capture the essence of these logical connectives in a very concrete way.
Yeah, they do. And this whole idea of proofs as programs was really driven home by that example of arbitrarily large primes.
Right, because you can't just say, oh, there must be arbitrarily large primes. You have to actually provide a method for finding them.
Exactly. That proposition translates into a type that requires you to construct something. Given any number, you have to construct a larger prime number and a proof that it's prime. And classical proofs often rely on things like proof by contradiction, which don't necessarily give you a concrete method.
So ITT is forcing us to be more constructive in our thinking. Now, you mentioned earlier that ITT has a more nuanced view of judgment than just whether a proposition is true or false. What are those different kinds of judgments?
Yeah, so in ITT, we're not just concerned with whether a proposition is true. We also have to judge whether something is a well-formed type, whether a term belongs to a particular type, and whether two types or two terms are considered equal.
Could you break down those basic judgments a bit more?
Sure. So the four basic ones are, first, asserting that something is a type. Second, asserting that a term has a specific type, which, under the propositions as types idea, also means that the term is a proof of that proposition. Third, asserting that two types are equal. And fourth, asserting that two terms of the same type are equal. And then we also have hypothetical judgments, which basically say, if we assume these things, then this other thing holds.
And you mentioned this connection to Kant's idea of analytic and synthetic judgments. How does the judgment that a term has a particular type relate to that?
Right, so Martin Loef, the guy who really developed ITT, he draws this parallel where judging that a term has a particular type is like an analytic judgment in Kant's philosophy. In an analytic judgment, the predicate is already contained within the concept of the subject. So in this case, the evidence for the proposition, the proof object, is explicitly given in the judgment itself.
So it's like saying this bachelor is unmarried. The concept of bachelor already contains unmarried.
Exactly. But the judgment of truth for a proposition in ITT, that's more like a synthetic judgment. Because to show that a proposition is true, you might need to actually construct a proof, and that might not be obvious just from the proposition itself.
So even logical laws, when you state them as propositions, they often require a construction, which makes them synthetic in this framework.
Yeah, which is kind of a mind-bending thought.
It is. And those analytic judgments, the ones where the proof is given explicitly, they have a special property, right? You said they're decidable.
Yeah, they are. Because of some really cool properties of ITT, like the fact that all computations eventually terminate and that you can always determine whether a term has a certain type, those analytic judgments are decidable. We can always figure out whether they're true or false.
Now, let's talk a bit about those meaning explanations. This idea of meaning as use, based on how we construct things and how we compute with them, that sounds very reminiscent of Wittgenstein.
It does, doesn't it? It's like the meaning is grounded in the use. So the meaning of the judgments in ITT is fundamentally tied to how we introduce objects of a certain type, how we construct them, and how we compute with them using those elimination and equality rules. And the central concept here is that of canonical forms, those fully simplified results of computation.
Can you give some more examples of those canonical forms?
Sure. So for natural numbers, the canonical forms are a zero and the successor of another canonical natural number. And for a function type, the canonical form is a lambda abstraction, a function that's ready to be applied.
And the computation rules, those are what tell us how to get to those canonical forms.
Exactly. Like beta reduction for functions and the recursion rules for natural numbers. They tell us how to simplify things down to their simplest forms. And the meaning of a judgment, like saying a term has a particular type, that's understood in terms of whether the computation of that term leads to a canonical object that belongs to the canonical form of the type.
So it all boils down to computation, to how things reduce down to their simplest forms.
Yeah, that's the core of it.
Finally, the material discussed mathematical models of ITT. What role do they play in understanding ITT's philosophical significance?
So those models, like the ones from category theory, set theory, and realizability theory, their main purpose is to show that ITT is consistent relative to other mathematical frameworks that we generally trust. If we can interpret ITT within these models, it gives us more confidence that it's not going to lead to any contradictions.
But you said earlier that models aren't the primary way ITT justifies itself, right? Because of those meaning explanations.
Right. While those models are important for relating ITT to other systems, Martin Liff's meaning explanations, they aim to give us a more direct, intrinsic understanding of why the judgments in ITT are valid. But some more recent models, like those based on groupoids and infinity groupoids, they've actually revealed some really deep and surprising connections between type theory and other areas of math, like homotopy theory.
And that connection to homotopy theory, especially Vygotsky's univalence axiom, that's really interesting from a philosophical perspective, especially when we think about the nature of identity.
It's a very active area, and there's a lot of philosophical depth there. The univalence axiom basically says that if two types are equivalent in the right way, then we can consider them to be the same within a universe of types. And that has some pretty big implications for how we think about mathematical equivalence and what mathematical objects actually are. It suggests a more fluid view of math, less tied to set theory.
So, to wrap things up, what's the big takeaway for a philosopher who's just encountering ITT for the first time? What are the core philosophical insights?
The main thing is that ITT offers a fundamentally different perspective on logic and math, one where truth is directly connected to constructive proof. It's not just about what's true in some abstract sense, it's about how we can actually construct proofs. And that propositions as types principle, that's really at the heart of it all. It connects logic, math, and computation in a profound way. ITT challenges our traditional ideas about existence and proof, putting the ability to construct front and center. And with all the exciting developments happening, like homotopy, type theory, and univalent foundations, it's clear that ITT is a vibrant and evolving field with deep philosophical implications, not just for math, but for how we think about knowledge and understanding in general.
Absolutely. And one final thought for our listeners. Given that ITT demands explicit construction for truth, how might that challenge or enrich our understanding of existence and possibility in other areas of philosophy beyond just math and logic? What does it mean to say something exists if we need to be able to, in some sense, construct it? That's something worth pondering.
Definitely.
Yeah.
It's a very thought-provoking question that could lead to some really interesting new insights.
Well, thank you so much for joining us for this deep dive into intuitionistic type theory. It's been a fascinating journey.
It's been my pleasure.